The best parts of chemistry are all about change, watching how something starts one way and ends another. But there are two types of changes we need to be able to kind of recognize and distinguish between in chemistry. That would be a physical change or a chemical change. A physical change may look like we change the stuff we're dealing with, but deep down to the atomic level, the composition is the same. We haven't rearranged any atoms, we haven't broken any bonds and reformed new ones. It's all the same material. Okay? Now, for chemical changes, we do change the composition. We end up getting down between the atoms and scrambling stuff up. Things bond to each other in different ways. We end up with new substances that have new properties. Okay? So something totally new with a different chemical recipe, different chemical makeup. Okay? So we're going to look at a couple different examples of how we can kind of clue in whether something is a physical or chemical change, starting with these two chemicals right here. Okay? So this guy is calcium chloride, and this guy is ammonium nitrate. They're just in these little cups here. They kind of look like Dippin' Dots. They are not Dippin' Dots, but they kind of look like it. Okay. All right, we'll go through these kind of one at a time, but I'm going to start both of these because they take a little bit while to get going. So I'm just going to mix some water in with these. Doesn't really matter how much. Just want to have enough to get it kind of dissolved. Speed this up a little bit. Just to give you a reference point. Okay. My water I have here, thermometer down in there, is 24.2-ish degrees Celsius. Okay. My chemicals in these cups are basically just sitting at room temperature, so something pretty close to that. Okay. Now, as I mix up my calcium chloride in the water, okay, I dissolve it so it starts to break into smaller and smaller pieces, right? Which means that it kind of gets lost in there. You think about dissolving salt in water, sometimes you stir it up and it just kind of vanishes, like it's gone. But it's not really gone, it's still in there. Mixing and dissolving are physical processes. Okay, so I'm going to mix this up a little bit, okay? And it's starting to kind of get lost in the water, like I was kind of mentioning with the salt. Now, if you've ever tasted salt water, it still tastes salty. So the salt is still there, the water is still the same. We've just put the two things together and mixed them up, and they look a little bit different. So that would be an example of a physical change. Okay? But sometimes mixing and dissolving can lead to a chemical change. Okay, I'm going to do the same for this cup here. Stir this up. Get this going. So we can come back to that. Okay, so first, I check the temperature of this. Okay, this hasn't gone up much, but it is significant. We're up to about 30 degrees Celsius. It's quite a climb compared to room temperature. Okay, if I feel the bottom of the cup, it's a little warm, and if I use more calcium chloride, I could probably get it, up to maybe 40 degrees Celsius or maybe even higher than that. Okay, so quite a bit of change. Now, I didn't go place this on a heater or anything. There was a chemical change down here at the atomic level with that calcium chloride in the water where some things rearranged. That released heat in the process. You can kind of think of heat as the waste of the energy world. So we have this extra energy left over from this chemical change that releases heat, and so everything in here gets hotter. Okay, so the water, the cup, whatever touches it, my hand, the table, heat is released out to that. Okay, so a good sign of chemical change is heat being released, your temperature rising, seemingly out of nowhere. Okay. Now, on the other hand, with my ammonium nitrate, I go and check this. My probe is still sensing kind of a high temperature. Drop that in my ammonium nitrate in water, and it's dropping precipitously. We're down to 16 degrees Celsius. It's still going down. We're down to 15. It keeps going and going and going, which is pretty chilly. Okay, and same kind of idea. I can feel the bottom of this cup, and it's a little bit cold. Okay. So even though the dissolving and mixing process was physical, it led to a chemical change. Okay, and I can tell because of the temperature drop. So in this case, heat isn't being released; it's being absorbed. Okay, heat is being stolen and sucked away from the water, the cup, the air, the table, my hand, whatever kind of comes in contact with it. Sometimes chemical reactions need energy, and so they'll take it from their surroundings. Okay, otherwise they'll usually be giving out extra energy to the surroundings. Okay, so not only is heat released a good sign of a chemical change, heat absorbed is a good sign of chemical change. So respectively, that could be a temperature change that goes up, we have temperature rising, or you have temperature dropping. Now these two chemicals actually have a commercial use. You can buy these, at any department store or hardware store. Calcium chloride is usually sold as a roadway salt, okay, like this guy, driveway heat, okay, and you can usually check the ingredients on the back to find where calcium chloride is listed, okay. Sometimes they'll use other similar chemicals like magnesium chloride, but for the most part, the most effective stuff is like this, okay. It's effective at melting snow and ice because as it dissolves in that little bit of water, okay, it releases heat, which melts the snow and ice. And once that's melted, you can now dissolve more calcium chloride in that water, which means you release more heat, which melts more snow and ice, which dissolves more, releases more heat, and it keeps going and going and going, okay, making it a lot more effective than something like just regular salt or sugar that just kind of lowers the melting point of the snow and ice. Now, that's a topic for a different video, but for now. So chemistry is not just done with things you can only get in a stockroom or in a lab. Sometimes we have stuff that's used every day. Chemistry is a tool for us and a resource for us. That's not just for lab work. Okay. Another example is the ammonium nitrate over here. Okay. You might see these kind of things called instant ice packs. Well, they don't really make instant ice, but they cool you off pretty instantly. Okay. What happens is you've got a baggie inside a baggie. The bigger baggie has a little baggie inside it. Okay, the little baggie has water. The big baggie has that little baggie and ammonium nitrate. When you squeeze the bag, you puncture the inside bag that has water and release it out to the bigger bag that has the ammonium nitrate. It dissolves, and that chemical change that happens once it's dissolved absorbs heat, sucks it away from whatever it's touching, like your skin, which can be soothing and relaxing for painful muscles or whatever is going on that you want a cooling pack for. Okay? So again, not all chemistry is strictly done in the lab. We use tricks like this everywhere in our daily lives. Okay, so heat being released can be a good sign of a chemical change, a good clue that a chemical change is happening. And right here, I have a lot of heat coming off of this. Okay, now does that mean that a chemical change is happening inside this hot plate to make the heat be released? No, maybe not. It's being powered by electricity. And in some simple terms, essentially I just have the electricity running around inside this hot plate, and that extra energy that's shedded off comes off as heat. Okay? Now, I have this water here in this kettle, and it seems to be very different than the water I'm used to. Usually, water is a liquid, okay, like this, and now I'm getting this stuff off of here. Now, it might be kind of hard to see, so I've got a glass beaker I can fog up. Okay, I can get inside it. Okay, you can see the steam there. Okay, now what we usually call steam is kind of a little tricky. We don't really see steam. We see little driplets of water. Okay, that's actually kind of the fog that comes out here. So our steam cools down enough to go back into liquid water here, which tells us something. even though I am making a gas from this, okay, I haven't really made a new substance. Okay, I started with liquid water. Okay, it gets real hot. Okay, and it comes through the end here of this kettle, and then out here it turns back into a liquid when it gets cool enough. Once that heat has kind of been released enough. Okay, so I go from liquid water to gas to liquid water, which means this gas is just liquid water too in the gas form. Okay, it has the same chemical composition. The only difference between a liquid and a gas, and a solid and a gas, and a liquid and solid, all those different phases, states of matter, okay, is how those particles move around. Okay, in the solid phase of matter, you have matter tightly packed together, and they can kind of vibrate in place a little bit. It can't do much more than that. Okay, if we give it enough energy, then they can start to do more than just vibrate. They can start to move a little bit. And they can start to groove. And they can start to slip past each other and roll around on each other. Okay? Even more energy allows them to not only move past each other, but also to start zipping around. They start flying. Okay? Which is what's happening here. All right? Our water gets enough energy absorbed from that heat, okay, that it can start zipping around and flying out of this kettle. And once it loses too much energy, it turns back into the liquid phase right here. Okay, so in any case, whether we're dealing with ice or what we usually call water as the liquid, or steam, okay, it's all just water. Okay, the chemical composition is the same, no matter which phase of matter you're in. So this is a physical change. Anytime you go through a phase change or a state of matter change, you are just changing how the particles move. Okay? Melting, boiling, freezing, condensing are all signs of phase changes, or all names of phase changes. So those are all physical changes. I've got a test tube of hydrochloric acid here. At first glance, it looks pretty much just like water, okay, which is a testament to, you should always assume something in lab is dangerous. You never know if it actually is or not, unless you know the substance, you do some testing and things like that. So this is concentrated acid. It's pretty dangerous, so I'm wearing gloves, and I'm going to be putting my goggles on here in a second. Okay, I'm going to drop in a piece of aluminum foil, just like this, all right, and see what happens. Okay. Now, I should get a gas released from this. So I'm going to cover this up with a balloon, so that way, if I do get a gas out, I can capture it. You can see it. Okay, well, so far, this is pretty boring. It's just kind of sitting down on the bottom of there. Now, our aluminum foil has a layer on the outside. You can kind of think of it like rust, but for aluminum. Aluminum oxide that the acid kind of has to work its way through. Okay, but once it does, we're going to start getting a couple bubbles. You notice that it's now floating, okay, as some kind of fizz is coming out. Now, this isn't a gas that's trapped, okay, somewhere in the liquid. It's a totally new substance. We put together a liquid and a solid, and all of a sudden we get gas. Now, if I get this a little bit closer, I might be able to see little bubbles fizzing. And now we got something going on. Bring this back a little bit. Okay, and there goes my balloon. So I'm capturing some gas up here, and this is getting too hot. Oh, I gotta put that down. Whew. Pretty good. Looks like things have calmed down a little bit. So just to give you an idea of how hot this got. I'm gonna touch the We're here, and it's climbing. 32, 33, 34, 38, 39, 40, 41, 2, 3, it just keeps going. 44, you get the idea. It's hot. Okay, so this reaction, this chemical change, released heat. Okay, which is one way we can tell it's a chemical change. It kind of tips us off there. It's something we already saw as a clue. Okay, but also we have a new clue to a chemical change, which is the fact that a gas showed up. Okay, out of nowhere. Okay, now if we are boiling something and we expect something to turn into a gas, then yeah, okay, we understand that is probably not from a chemical change. That is a physical change, okay? Still dealing with the same substance, but now its particles are moving fast enough to escape into the gas version of that pure substance. But in this case, it got hot, but not really hot enough to boil the liquid down here. If it did, then that would have to reach 100 degrees Celsius, right? That's the boiling point of water. Hydrochloric acid's boiling point is probably a little bit different, but it's got to be pretty darn close since it is dissolved in water. So what this tells us is we're going to get gas from something that wasn't originally there. Okay, this is a new substance. Okay, and that is a sign of a chemical change. Okay, we sometimes call this the evolution of a gas. Okay, or we say that the gas has evolved out of the reaction mixture. But the presence of a new gaseous substance is the sign of a chemical change that we're seeing here. Okay, so we've got another clue to add to our list. I'm going to break a rule of lab for this one. I'm going to break a fundamental rule, okay? You should never eat or taste anything in the science lab unless specifically told you can taste or touch or, whatever, eat this specific thing. And so in general, you should never put your mouth on something that a chemical is on the other side of, like a pipette or anything like that, okay? Now, I'm going to do just that. I've got a straw here. I've got a flask of a liquid we call universal indicator, okay? And like the name suggests, it indicates, okay? And typically in chemistry, indicators are meant to show how acidic or basic something is. You're probably familiar with some common acids, the things in your food and drink that taste kind of tangy or sour, okay? You've got hydrochloric acid in your gut, okay? That's your stomach acid, and it's what I used to react with that aluminum back there. Bases are, you can kind of think of like the opposite of acids, okay? They work kind of the other direction. You find them in a lot of cleaning products. They tend to have kind of a bitter smell and are a little bit slippery feeling, okay? But, that's a whole nother video. So all you kind of really need to know at this point is acids and bases kind of work against each other, okay? And we have chemicals that can show how acidic or basic something is. Now, some simple acid-base indicators just change from one color to another, so maybe from clear to pink or from red to blue. But this guy, universal indicator, is special because it goes through a whole range of colors, okay? Now, to kind of show you an example of this, I'm going to blow bubbles into this, which again, you should not do. Okay, unless you are kind of a licensed professional or someone has specifically told you it's okay. So do better than me. I also wear goggles during this too, but here we are living dangerously. So as you can see, we're starting off with kind of a green color. It's a very dark green. I can get a little bit closer here. Got a dark green color. So let me start blowing bubbles into this. Now, what am I breathing out? Well, I'm breathing out carbon dioxide, right? CO2, all right? Now, CO2, carbon dioxide, does not have a color, okay? And yet, my stuff is now yellow, which is a little weird, okay? So something's going on here. Let's keep going. I'm going to continue to breathe out CO2 into this. All right, I've made it to kind of a reddish-orange color. Okay, so what's going on here? Well, if you think about a can of soda, all right, that has some fizz in it, right? It's pressurized, it's carbonated. Okay, we do that with carbon dioxide. Okay, now when that carbon dioxide is shoved in there, it's not only just becoming fizzy, in between the particles of liquid, it also makes a substance called carbonic acid. Okay, so we blow CO2 into something and it can make an acid, like carbonic acid. It also gives it kind of a tangy flavor. Okay, if you've ever noticed that when your pop goes flat, it tastes sweet. Well, when you're losing that fizziness, you're losing that CO2, it's kind of moving out of the liquid. You're also losing that carbonic acid that was made from the CO2. So you lose that tangy flavor and you get just kind of the sweetness of all the sugar that's crammed into that can. Okay? Well, as I blow CO2 into this, okay, I am making something acidic. Okay, I am making carbonic acid, which is a new substance. Okay, and my indicator works by reacting and changing to a different chemical with a different color. I'm not blowing red into this. I'm not adding another color. My straw is not dissolving and giving off some color or something like that. Okay, the color seemingly comes out of nowhere because I'm making a chemical change. Okay, that results in a new substance with a new color. Okay, a lot of chemical changes seem to happen like magic. Okay, like there's no way it could have happened, and yet it did, okay? It's like smoke and mirrors or something. So this is a good clue of a chemical change, a color change seemingly out of nothing. So a color change can be a good sign of a chemical change, okay? But does that mean every time we see something change colors, it's going through a chemical change? Not necessarily. Okay, we need to be careful about where that color comes from. Okay, if the substances don't change, then we're just kind of adding something that already has a color to something else. So say for your pencils use graphite, okay, which is just a form of carbon that you break into little tiny pieces and smear across your page. Okay, that streak gives you, your writing. Okay, it's how you write in pencil. You're just basically breaking off a little piece of this graphite stuff. I've got a big piece here, but it works essentially the same. So I can write with this. See my beautiful artwork. Okay, now I have not changed what the graphite's made of, and I haven't changed what the paper's made of. If I get a rubber eraser, I can rub those little bits off of the paper and almost totally reverse it. It's usually not perfect, but it's pretty darn close. Okay. Same goes for markers and painting and things. If I take this blue marker to my goggles and give myself some nice eyelashes. There. Like that. Let me see how well it turned out. Oh, look at that. I got beautiful eyelashes now. Now, I haven't changed what the goggles are made of. I haven't changed what the ink is made of. I've just put one thing on another. I haven't changed my goggles to be some new chemical that's blue. I just put something blue on them. And a good way to check and see if this is actually from a physical change or a chemical change is to see if you can reverse it. Okay, if I can wipe this marker off, that material is still there. Okay? So if you are adding on a color that already exists or mixing existing colors, like mixing red and blue paint to get purple paint, that is a sign of a physical change, not a chemical change. So you have to be careful about where your stuff comes from, okay? And what actually changes. Is it down to the nitty-gritty of the atoms, or is it just, looking something a little bit different? This is magnesium metal. In this case, we've got it as a big ribbon. Okay, kind of pull out pieces like this. Like most metals, it is kind of gray and shiny. All right. Get a piece around there. It's also pretty flexible, so it can be reworked into different shapes. But unlike some metals, this is also able to be cut pretty easily. All right. So I can just take a regular pair of scissors. I'm just going to snip off a piece right there. Okay. Now when I do this, I'm not changing the magnesium to some new substance. I'm not changing anything about the scissors. I'm just making a smaller piece of this, kind of like breaking off little bits of that graphite. Okay, so anytime you are cutting something, or breaking something, okay, ripping something, tearing something, that is all a sign of a physical change. Okay. Now I can get a chemical change to happen with this, and I actually already have the ingredients already with me. Okay, I need the magnesium and the oxygen that's already in the air. Okay, I can essentially burn this magnesium by getting it to react with the oxygen in the air. It's taken a little too long just waiting for it to happen as is, so I'm going to speed it up. Okay, I'm going to give this a little bit of a kickstart with a lighter. There we go. Okay, so I'm going to turn the lights down and do this in a separate take. If this were in person, I would have to tell you that you shouldn't look directly at it because we're going to see some bright stuff, and some of the light released from this is going to be UV, which is not good for your eyes. But since you're watching this through a video, it's not going to matter. So unless you don't want your screen to be very bright all at once, then you might want to be careful of that. Bring this closer. The lights are down, but you might be able to tell this is no longer a gray kind of metal. And if I touch this down here, it just breaks apart. Okay, it's no longer nice and flexible. I've got this white powdery stuff. Okay, and this is a different chemical compound entirely. It looks different. It has different properties. We had signs of a chemical change with the heat released. Okay, and the color change that happened is now white instead of gray. We also have a new clue of a chemical change, which is light being released. There's a whole bunch of light being released from this. Okay, so we've got another clue to add to our list. I have a balloon here I'm going to blow up. Again, I breathe out CO2, and my balloon gets larger. Its volume increases a lot. Now, does that mean that I'm changing what the balloon is made of? Do I have more mass? No. Inflating the balloon just stretches out the material we have here. You can tell that it kind of thins out, okay? Just kind of, it becomes a little bit more translucent. You might be able to see my hand back here compared to when it's a little bit smaller, a little bit thicker. Okay, so the rubber that a balloon is made of is called a polymer. It's essentially a bunch of big, long chains of atoms that can be kind of pulled taut and released to kind of crunch up and then back and forth like a rubber band. Okay, well, in this case, we have a pretty stretchy, elastic polymer to make this balloon, right? Which means it has a little bit of give. It can stretch a little bit. Okay, so this isn't going through a chemical change. This is just stretching out the material that's already there, and we see it gets thinner a little bit as it goes. So blowing up a balloon, inflating it, stretching things in general is a good sign of a physical change. Okay, the material's still the same. Okay, I've just kind of pulled it apart into a thinner layer. Okay, now we all know, probably just by personal experience, what it's like when a balloon pops. So I've got a very pointy stick. Just
point that in there. Oh, well, I mean, you guys have probably already seen a balloon pop before, so yeah, that'd be kind of boring to show you that. So maybe I'll do something a little bit different. Okay, there's my skewer on the other side. Just to go. There it is. We've got a balloon on a stick. Okay, now if it did pop, then we'd have little shredded bits of balloon everywhere and make a loud noise, and as the air moves away and stuff like that. So we could also go on and say, yeah, okay, if the balloon breaks, then that's also a physical change. But I just thought this was a little more interesting. Since your balloon is made of a stretchy material, okay, if you still have a little bit of give left, okay, it can still stretch a little bit. Piercing it with a sharp object like this skewer, you can just get it like a department store, means it can still stretch a little bit out before it just is too thin and rips. Okay, the best way to do this is to go through the bottom of the balloon where it's thickest, where it's darkest. Okay, where you see you still have some rubber polymer to stretch around. Okay, and to kind of hold tight around that so it doesn't leak. And same at the top, where you've got kind of a dark part there. You want to go through the bottom and through the top. Okay. If you can't get it to work, your balloon might be a little too big. You might try adding a little bit of like dish soap or something to kind of slick up the skewer, so that way it has less friction and it's got a better chance of making it through without tearing the balloon. Okay, so this is a neat little party trick that you can go and amaze your parents with, or other people that haven't taken my class. If you show it to someone who has taken my class, they're like, "Oh, Mr. McCord already showed me that. I know." But it's kind of neat. Okay? Kind of a fun little thing you can do on a Friday night. Okay, so anytime something is stretching or breaking, tearing, that is a good sign of a physical change. I've got a couple chemicals here. One is called lead nitrate. Okay. The other is called potassium iodide. And I'm going to be mixing them in this beaker here. I'm going to start with the lead nitrate. I'm just going to pour some in the bottom here. Okay, and as you can tell, it's clear, it's colorless. It looks just like water. Okay, this is a solid dissolved in water. Okay, so you can't even see it anymore. Okay, and I'm going to add in and mix this potassium iodide with it. Now remember that mixing alone is not a sign of a chemical change, it's a physical change. But sometimes mixing chemicals can lead to a chemical change. So I'm going to drop a little bit in with this pipette. Cap that. There we go. Get nice and close so you can see this. Now my potassium iodide is a little bit yellow, but it's for the most part pretty clear. Okay, so not much different there. Okay, so watch closely. So add a couple drops of this in. Ooh, okay. Okay, let's do a little more. Look at that. I'll do a whole bunch at once. Here we go. Okay, well, we've got a sign of a chemical change in that we've got a color change. We've got this brilliant yellow color stuff in here. Okay, so not only are we mixing stuff, that mixing has led to a chemical change between the stuff that we're mixing. Now you might notice that this yellow stuff is kind of settled at the bottom here, okay, which is a little interesting. Okay, that's actually a solid. Okay, we put two liquids together and we got a solid. Okay, we call this precipitation. If you think of it like rain, rain precipitates out of the sky. It's like a liquid coming out of a gas. In this case, we've got a solid raining out of a liquid, which is kind of wild. You can even see this kind of clearing up at the top. It's kind of like pulp at the bottom of your orange juice. Okay, so this solid down here must be a new chemical, not just because of the different color, but also the fact that we have a solid suddenly out of nowhere, out of two liquids. Okay, this is a good sign of a chemical change. Precipitation is a sign of a chemical change. All right. Now I can also go and separate and filter this off. Okay, I can take the solid and get it out of the liquid by pouring it through a filter like this. Okay, I've been doing this with a couple other samples I did in class. So I've got this liquid down here, okay, that is kind of separating out on the top, and I've also got filter paper, okay, and that is my chemical solid that I've made, my new substance, my product, which is in this case lead iodide. Now they actually used to use this stuff for yellow paint, okay, because of its beautiful color, but problem is it could give people lead poisoning because of the lead content inside it, so not so much anymore. Now it's just kind of used to teach chemistry. Okay? But it is a really nice color. Okay. Now when I filter this, I'm not changing the chemical composition. It's still the lead iodide that I made from this chemical change, this chemical reaction. Okay. The only thing that's different is I've taken the solid and the liquid and I've put them in two different places. In this case, with a filter that has holes, okay, pores that are small enough to let the liquid through, okay, but not the solid. Okay, the solid is too big, the liquid is small enough to make it through. Okay? If you do this in a small enough concentration, you can actually get a different version of this reaction. You've got, it's like these little sparkles. I wonder if this will show up. I can try and shake this a little bit. Got these little golden sparkles floating around in there. Just kind of cool. You can find some really cool videos and pictures on the internet of that. Mixing lead nitrate and potassium iodide to get lead iodide. Okay, so we've got a new clue for a chemical reaction. Okay, precipitation, getting a solid out of seemingly nowhere, usually between two liquids.